Yeah, so it's recording. So if it is recording, then I should share my screen. I am sharing my screen. Yeah, thanks for reminding me to record. Okay. Now, today, we want to look at estimation. 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 You know, as statisticians, all the time, we keep on talking about estimates. Why do we talk about estimates all the time? And I can see the pen is not very black. Let me check on it. Why do we talk about estimation all the time? It's because sometimes you need to know a particular measurement about a particular population. Suppose the population is made up of 40 million, then obviously you cannot interrogate each and every member of the population. So you may take a sample in order to obtain a value which you can say represents the true population parameter. So this value that we get from a sample, which is known as a statistic, is actually an estimate. It is actually an estimate. You know, conducting, unless it is a population census, like if we want to know how many Kenyans how many Kenyans are how many Kenyans there are, then obviously for that one, you may not really take a sample. And that's why we usually talk about a census. When you do a census, you count each and every individual. But when we talk about a survey, then you are really looking at just a small fraction of the whole population. Now, conducting a census is quite expensive and it is time consuming, and you may find that you need highly skilled personnel who of course attract large monetary benefit. So instead of sometimes conducting a census, then you just consider a sample of the population, and then of course you come up with an estimate of the true population value, which we usually refer to as the population parameter. So today we want to look at estimation. We are looking at estimation, and we can therefore just note that there are two types of estimates. There are two types of estimates. The first one is a point estimate, and the second type of estimate is an interval estimate. Just to explain, a point estimate can be like X bar is equal to, let's say 30. X bar is equal to 30. That is a point estimate. That's a point estimate. That's a point estimate. One particular value. What about an interval estimate? When we say that maybe X bar lies between 60 and 40, then we are actually giving an interval estimate. So this is just the difference between the two. So now let's move on to methods of estimation. Methods of estimation. That's our subtitle, methods of estimation. Now, there are 4 major methods of estimation, but we shall only look at one method. We will look at one method which is commonly used. We will look at the maximum likelihood estimator method. Maximum, I'll write that in short, maximum likelihood maximum likelihood estimator method. So this is the method which is commonly used. Let's just make one definition. You can see I've written there likelihood. So what is likelihood? When we say likelihood, what are we referring to? So definition, likelihood function. So what is a likelihood function? We define let x1, x2, x2 up to n be a random sample from a population with density function. Now we are experts of density functions. So be a random sample from a population with density function. Which density function? F of x theta, f of x theta, be a random sample from a population with density function f of x theta, then the likelihood function of the sample values is their joint density function. Which one? L of x theta. This is the likelihood function. So when I write L of x theta, of course, x represents the sample values. It represents the sample values, and theta is the parameter of interest. Like, remember when we were talking about the Poisson distribution, and we said that lambda was the rate parameter. So in general, we just want to denote the parameter of interest by theta. So this likelihood function, as we've been told, is the adjoint density function. That is, L of x theta is equal to f of x1 theta x1 theta multiplied by f of x2 theta up to f of xn theta, f of x n theta. Now, how do we show those products in short? We have this symbol, which is for product. It is for product. It is not pi. It is product. From I is 1 up to n, f of xi theta, f of xi theta. So this is how we can denote equation 1 in short. We can denote equation 1 in short by the product function of f of xi theta. So we can just note that the first note, we note that if the likelihood of theta hat, in statistics, when we put hat, it means it's an estimator of the real value. So we are noting that if L of theta hat, which is read as the likelihood of theta hat, so I'm saying that if the likelihood of theta hat is greater or equal to the likelihood of theta, then theta hat, then theta hat is the MLE. Then theta hat is the MLE. What does that stand for? Maximum likelihood estimator. Then theta hat is the MLE of theta. MLE of theta. What am I saying? I'm saying that if we identify the maximum likelihood estimator, which we shall denote by theta hat, then when we substitute this theta hat in the likelihood function, we always find that the likelihood function is either greater or equal to any other value of theta. And that is why this theta hat is being called the MLE of theta, because it maximizes the likelihood function. Again, we note the second note. Therefore, we maximize. You know, whenever we talk, whenever in mathematics, calculus, and other things, other units that you've been taught before, whenever we talk of getting the greatest or the lowest, we always remember that we must perform differentiation. When we differentiate, we either get the maximum possible value or the minimum possible value. Now we are looking for the maximum likelihood estimator. Therefore, the second note is that we maximize dl d theta. We maximize dl d theta or d ln L, the ln of the likelihood d theta. I know that you engineers usually call natural log as ln. So this ln represents natural log, and we know that natural log is usually log to base e. It's usually log to base e. So I'm just saying that for us to identify theta hat, we differentiate the likelihood with respect to the parameter of interest, or we can also differentiate the natural log of the likelihood with respect to the parameter of interest. So we can note the third one, that given sample values, we obtain the estimate. Given sample values, we obtain the estimate. Given sample values, we obtain the estimate. So what I mean by the third note is that once we found the maximum likelihood estimator, then if we are given some values like x1 is 1, x2 is equal to 2, then we can get an estimate in numerical form. And we shall see this as we look at some examples. So the first example, let me write from the top so that I maximize on space. The first example, given the following PDF, f of x theta being equal to, this is f of x theta being equal to theta x raised to theta minus 1 . I hope it is clear. This is theta minus 1. It is raised to, x is raised to theta minus 1. Let me try to make that clear. Theta minus 1. This is a comma. I'm just trying to say that where x is less or equal to 1, greater or equal to 0, so I can put my comma there, and theta is also supposed to be greater than 0. So theta is non-negative. Theta is greater than 0. The questions are, part 1, we find the MLE. We find the MLE theta hat. Find the MLE theta hat. We need to find theta hat. And then secondly, we shall find the estimate theta. We will find the estimate of theta given x1 is equal to 0.77, x1 is 0.77, x2 is equal to 0.82, x2, let me just write it in case someone gets lost, maybe network problem. X2 is equal to 0.82, x3 is 0.92, x4 is 0.94, and x5 is 0.98. x5 is 0.98. So first we need to get the MLE theta hat, and then after that we can get the estimate of theta. We can get the estimate of theta. So first of all, let us get the MLE. Now we have been given f of x theta as theta x raised to theta minus 1. So now we need to get the likelihood function, LXI theta. You know the xi's keep on changing in value. So this will be as shown in equation, let me call it equation 2. It is we need to get the product function. So what this means is that we are getting the product function from I is 1. The product function from I is 1 up to n of theta x of I raised to theta minus 1. So this is not challenging. Let's do it. So now when I takes value 1, what are we going to have? We shall have theta x1 theta minus 1. That is when I takes value 1. When I takes value 2, we need to multiply what we have written by theta x2 theta raised to minus 1. And we shall do this when I takes value 3, we shall have x3. When I takes value 4, x4. And we shall do this until the last term where I will be taking value n. So x again is raised to theta minus 1. Now let us just simplify that equation. So of course, if we multiply theta n times, theta will be raised to n. And then looking at that equation, we can see that x1 is raised to theta minus 1, x2 is raised to theta minus 1, and so on up to xn is raised to theta minus 1. So we can write this as x1 multiplied by x2 multiplied by, and so on up to xn. All this product will be raised to power theta minus 1. Theta minus 1. So now we have our likelihood function. We have our likelihood function. And our parameter of interest is theta. Our parameter of interest is theta. So we need to differentiate L with respect to theta. We need to differentiate L with respect to theta. And we can try to make this, looking at that expression, if we differentiate directly, we may run into some problem because we can see that theta is in the power. So to make it easier, we take ln. So taking ln is optional. If differentiation would not be tasking, then we would just go ahead and differentiate. You will see that in even some of the questions that I'll give you for exercise, you'll find that in some expressions, you can easily go ahead and differentiate. But in some cases, you may find that it is easier to differentiate after taking natural log first. So for this particular problem, because theta is in the power, we can take natural log first. So ln L is equal to n ln theta plus theta minus 1 plus theta minus 1 ln x1, x2 up to xn. Up to xn. Then after this, now we can differentiate. Now we can differentiate. So we get the ln L d theta and this will be equal to n over theta minus, we are differentiating with respect to theta. So if I open this bracket, I will have theta in front of theta just before ln that. So if I differentiate that, it will be plus ln, because you're differentiating with respect to theta, ln x1 up to xn of course minus 0, because the other term, if we open this bracket, we will have negative of this, negative ln the quantity in the bracket, and there is no theta, so that should just be 0. And you know, if we want to maximize, then we need to equate that expression to 0. So doing that, we will find that if we simplify, we shall find that theta hat is equal to, theta hat is negative L over theta will be equal to negative ln x1 up to xn, that product. So theta hat will be equal to n over negative ln x1 up to xn. x1 product up to xn. So I can as well have this negative of hours in the numerator so that it's more visible. So it is just negative n over ln. So this is our MLE. That is our maximum likelihood estimator. And you can note that once we get the maximum likelihood estimator, then we need to give it a hat, which shows that it is an MLE. It's an estimator. It's an MLE. Okay, so let's answer the second part of the question, which requires us to obtain the estimate given what? Given these values. Given the values x1 up to x5. So we simply substitute in equation 3. I will call this equation 3. So it means that our estimate theta hat will be given by n refers to the sample size, so it's minus 5 because we had a sample of size 5 over natural log of we have to multiply these numbers. 0.77 times 0.82 times 0.92 times 0.94 times 0.98, and then we get the natural log. We get the natural log. And so if we get the natural log, then you'll find that what we have is 5 over 0.6253. 6253. And so theta hat, the estimate is 7.99. 7.99, which is approximately 8. So it means that this this PDF of ours, f of x theta, it means that at the position where we have theta, then the best estimator is 8, is the value 8. The MLE, the maximum likelihood estimator, is 8. So that is one example of how we obtain the MLE, and we also obtain the estimate. Now let's look at another example. We look at another example. We look at another example. Find the MLE. Find the MLE for lambda. Find the MLE for lambda. I've written lambda there. MLE for lambda. For a Poisson distribution with PMF, for a Poisson distribution with PMF, f of with PMF f of x f of x lambda equal to E minus lambda lambda raised to power x over x factorial and of course for the Poisson, you know, x starts from 0, 1, 2 and so on. X begins from 0 followed by 1, then 2 and so on indefinitely. So let's get the likelihood function, then we shall then we get the MLE. Now the likelihood L of x theta, sorry, not theta, L of x lambda, you know, it is the product from I is 1 up to n of f of xi lambda from I is 1 up to n f of x lambda. So if I is 1, then we have E minus lambda lambda raised to x1. Why x1? Because the likelihood is L of xi lambda, L of xi lambda. So when x takes so when I takes value 1, we have E minus lambda, lambda raised to x1 over x1 factorial, x1 factorial. When I takes value 2, Then we have E minus lambda. Of course, we are multiplying because it's a product function. E minus lambda, lambda raised to x2 over x2 factorial. And this continues until I takes value n. So we have E minus lambda, lambda raised to xn lambda raised to xn over xn factorial, the last term. So let's try to combine this and see how we handle it. So this simplifies to e raised to, we are adding minus lambda n times. We shall add minus lambda how many times? N times. That power there, this one here, that one there. So it will be minus n lambda. E will be raised to minus n lambda. And lambda will be raised to, we will add x1 to x2 all the way up to xn. So that will be summation I is from 1 up to n of xi. And then what happens to the denominator? We have product. This is product function of xi. So the xi's which shall be multiplied, each of them factorial. So this is xi, not x1, product of xi's factorial. Now again, for easier manipulation, we take the natural log. So ln L will be equal to minus n lambda plus summation xi ln lambda and when we are dividing, we usually when we divide, we subtract the lns or the logs. So minus ln of the denominator, product function of xi factorial. Okay, so now we can differentiate with respect to the parameter of interest. We want to get lambda hat, the MLE. So we now differentiate the ln L with respect to lambda. And so what is that equal to? It will be equal to minus n plus summation xi over n minus, of course, 0. And we need to equate this to 0. That differentiation, we equate it to 0 in order to obtain lambda hat. So lambda hat will be none other than Okay, I can see I wrote something wrong there. When I was getting d ln L, d lambda, differentiating the first term, I get minus n plus summation xi over lambda. But what did I write? N. Sorry for that. If you copied that, that's wrong. It should be summation xi over lambda. Sorry for that. So now we can get our lambda hat. So lambda hat will just be summation xi over n. Summation xi over n. If we solve. And with the statistics that we have been doing with you since day one, you know that summation xi over n is equal to x bar. So the maximum likelihood estimator is x bar. Okay, now let's get an estimate. Suppose we were given these values. Suppose x1 was 1, x1. Now we are trying to get the estimate, the actual numerical value. Suppose x1 was 1, x2 was equal to 1, and x3 was equal to 0. Suppose we had just a sample of size 3. So what is lambda hat? Lambda hat, according to equation, what I'll call equation 1. According to equation 1, lambda hat is just summation of xi, that is summation of the observations, as in 1 plus 1 plus 0. And then we divide by what? By the sample size, which is 3. So what is that equal to? It is just equal to 2 over 3. So that is lambda hat. So this is how we handle questions on maximum likelihood estimation method. Maybe I will send, it's not maybe, obviously I will send at least 2 questions. At least 2 questions I will send for your practice. In the first question, you will obtain the MLE without getting the ln. It's possible. And in the second one, maybe you can consider you can consider taking the ln. But in the first one, you can just differentiate without taking the natural log. Okay, so we continue. So I said that in estimation, we have 2 types of estimators, the point estimator and the interval estimator. Now, like this value we obtained, which is 2 over 3, this is a point estimate, or a point estimator for that matter. Now, we go on to interval estimators, and so our subtitle now is confidence intervals. Confidence intervals. So, statisticians usually conduct research, and then they may, it's not a question of may, they have to give the results to the interested party. So Sometimes you'll hear statisticians on television like Ipsos Synovate, who usually give us results of surveys that they have conducted. So when they give us results and they say that the mean is equal to this, the question is, what is the confidence level? What is the confidence level? How confident are they that that value they are giving us is statistically acceptable? You know, for results of a statistical experiment to be acceptable, some rules and laws must be followed and satisfied. One of them requires that when you give your results, you may have to state your level of confidence. So what we can just bear in mind is that a sample mean X bar is not always equal to the population mean, is not always equal to the population mean mu due to sampling error. So sometimes you may calculate X bar, but it is not actually equal to mu due to some errors which arise as a result of using a sample. And we call those errors sampling errors. Now, confidence intervals are ranges of numbers. Let me write that. Confidence intervals are ranges of numbers that have a high probability of containing the unknown parameter. The population mean mu may or may not lie in the confidence interval obtained. The population mean mu may or may not lie in the confidence interval obtained. So, just to illustrate briefly, suppose we had some measurements and one of these measurements happens to be the population mean mu. Suppose that is the population mean mu. So there are other values. There is a value here. Sorry, how do I want to write that? I didn't want to write 2. there are values to the left of mu and to the right of mu. There are values. It doesn't really matter what the values are, as long as some are to the right and some are to the left. Now, suppose we give a confidence interval. Let's say this is the first confidence interval. So we are saying that the population mean may lie between the two ends of that line, or again, maybe it lies between those two values, or it lies between these values, the third set, and then we have another fourth set of values. And we have a fifth set of confidence interval. Now, what we realize from this diagram is that mu is included in 4 of the confidence intervals. In 4 of them, the population mean mu actually falls between the intervals given, only for 4 of the intervals. But for the fifth one, mu does not fall within that confident interval. So we are seeing that 4/5, in 4/5 of the confidence intervals, the population mean falls within those confidence intervals. So what level of confidence do we have, or how sure are we that the mean, population mean, will fall within the given confidence intervals? Because only 4 out of 5 of them contain the population mean mu, then we are 80% confident that mu will fall in a particular given confidence interval. So this is now why we're talking about confidence intervals. What we want to see next is performing some computations and giving particular confidence levels. So when we talk about confidence interval, this is what we have in mind. How sure are we that the population mean will fall within the given confidence, within the given range of values? We can see this, we will understand this more as we perform some computations. So we usually calculate confidence intervals depending on some values, or depending on information that is given. So in the first case, in the first case, we want to consider confidence interval for mu, confidence interval for mu, when sigma is known. When sigma, and now you know that sigma is standard deviation when sigma is known. That is when we are given the value of sigma. Confidence interval for mu when sigma is known. Now, the confidence interval is usually given by x bar plus or minus z alpha over 2 sigma over square root n. So if you are seeing there z alpha over 2, then now remember we have been learning how to read values from those tables. And so even right now, it will become important, useful, the knowledge we learned on how to read the values. Okay, so example, construct 90% confidence interval. Construct 90% confidence interval for a sample of size 40, for a sample of size 40 from a population which is normally distributed, with mean 54.89, with mean 54.89, and variance, Bill, I've seen your correction, and variance equal to 57.91, and variance equal to 57.91. So I was saying that 90% confidence interval, sample size 40. What is the mean? 54.89. 54.89. That is the mean. Sample size, which is n, is 40. And population variance is given as population variance, which is sigma squared, is given as 57.91. 57.91. So we need to get what? 90% confidence interval. 90%. So we need to go back to our lovely tables. And before we go there, we need to think a little bit first. You see, we want a 90% confidence interval. What does that mean? That the middle area is 0.90. So we need to identify the z-score value to the right. And of course, it is also equal to the z-score value on the left, only that the one on the left is negative. And that is why we are calling it Z alpha over 2. You know, so why are we talking about Z alpha over 2? This area here is alpha over 2. Sorry, the area to the right, let me not say here. The area to the left, extreme left, is also alpha over 2. That is why we are calling this z-score value as Z alpha over. So we need to go to our lovely tables, and we get Z alpha over 2 such that the middle area is 0.90. Before we go there, remember that from minus infinity up to Z alpha over 2, that area will be 0.9. I don't know whether I'm right. What is 1 minus 0.9? 1. Anyway, alpha over 2 plus alpha over 2 is 0.10. Because that comes from 100% minus 90%. That is 10%. So we need to divide this by 2. So what is that? 0.05, if I am not wrong. So this area here is 0.05. So, okay, 0.05. So it means that from minus infinity up to Z positive Z alpha over 2, that area should be 0.95. Why? Because the middle area is 0.90 and the area to the left is 0.05. So when we go to the tables, we will look for z-score value for 0.95. Let me also open my tables so that you can see that I also know how to read that. I don't know whether it's taking long to open. So where is that? We are looking for normal. (0.95). It's opening up. I share my screen. So there it is. Maybe wait a little bit so that everybody can receive. So you see the curve at the bottom for an area from minus infinity until 0.9500. If I look at 1.6 on the left, I can see 0.94520. I go on, then 1.6, okay. 1.6, we can see 0.949 followed by 0.95053. So we can take either of the two. Please, we do not extrapolate. We can take either of the two. So suppose I take the first one, 0.94950. If it is rounded off, it comes to 0.95. If it is rounded off to 2 decimal places. So we can see that one is 1.6 at the top. There is 0.04. So it is 1.64. 1.64. So we are saying that this z-score value is actually equal to 1.64. And so that's it. Now we can go back to our question. So to get the confidence interval, we simply substitute in the formula, which I can call equation 1. So we substitute in equation 1. We know our z alpha over 2 value. So now the confidence interval will just be x bar 54.89 plus or minus z alpha over 2 is 1.64 is 1.64. What is sigma? Square root 57.91, 57.91 over what? Over square root n, that is square root of 40. And so we get two values. Because of the plus and minus, we find that our confidence interval is 52.92. Yes, there is a question. Majestic. We don't interpolate. We don't interpolate, please. We usually take either. So that means that when we are marking, we have to make room for students who took one value against another. We don't interpolate. You will not get any mark for interpolation. Maybe you do that in engineering, yes, and in some mathematical units also, there is a bit of interpolation, but when we are just reading the values in the table, we usually take the one which is nearest. So that's the rule. So we do that. So you see, somebody could have taken, where's the table? 1.6. Someone could have written 1.64, and someone else could have written 1.65 as the z alpha over 2 value. So when we are marking, then it means I should accept two different answers depending on the value that any of us read from the table. So our confidence interval is 52.92 up to 56.86. Yes, there's another question. Let me write that properly. Okay, Stephanie is asking, aren't we supposed to use area to the left for normal distribution. I think Stephanie is coming from those examples that we were doing last time. Let me explain this. Let me explain again what I said so that maybe it can be clear. You see, let me go over it again. Now, the confidence level should be 90%. And we are looking for confidence interval. Now, if we are looking for a confidence interval, it means that we need to give some two values, say A and B, so that the population mean should lie between those two values. Now, the confidence interval must be balanced. So it means that if it is 90%, confidence interval, which gives us a 90% level of surety, then 0.90 should fall in the middle of the normal distribution. I know last time when I was teaching you how to get particular areas to the left, particular areas to the right, to get z-score values, whether if it is for a particular area to the right, a particular area to the left. Please detach yourself. I mean, we are not doing that anymore. I was doing that to give you practice, to train your mind to understand how we read these values. Now we have come to a real application case, and we have to reason. So right now, there is no question of saying either to the left or to the right. We want a confidence interval. So the confidence interval can either be, it will be two numbers, A and B. But how do we determine those two numbers? If we want a 90% confidence interval, then the area in the middle should be 0.90. Then the area to the right should be 0.05. The area to the left should also be equal to 0.05. Why am I saying this? Because I know that under the curve, the total area should be equal to 1. And so if the middle area is 0.90, and it is in the middle, then it means the area to the left and the area to the right, they are equal in magnitude. That is why we are talking about Z alpha over 2 value. So in this question of ours, what is the value of alpha? The value of alpha in this question is 0.10. How do we get 0.10? It is 1 minus 0.9. So when we get that 0.10, now we know that this 0.10 is for, it should be divided between the area to the right and the area to the left. That is how we get 0.05, 0.05. So why are we doing that? Because we want to get the Z alpha over 2 value. So we have already identified that alpha over 2 is equal to 0.05. And now we want to get the z-score value, which is such that the area to the right of the z-score value is 0.05. For us to read this positive z-score value, remember the way our table behaves for the standard normal. Let me show you. Remember how it behaves. If you look at this diagram drawn at the bottom, you can see the shaded part. Why is that part shaded? Because those numbers that we are seeing inside the table, they are representative of the shaded part. And that is why I keep on saying that from minus infinity up to a particular value. From minus infinity up to a particular value. So if I can go back to my whiteboard, this is why I said from minus infinity up to this z-score value. You know, we want to find positive z alpha over 2. To find that positive z alpha over 2, we must remember that the black part is from minus infinity up to that positive z alpha over 2. Now, we know that the area to the right of the z alpha over 2 is 0.05. So what is the area from minus infinity up to z alpha over 2? It must be 0.95. So let me repeat again. When we are answering these questions, we reason afresh. What we were doing last time, I was just giving you practice on how to read the values. You can see the level of thinking that is involved. You must understand the question and you must know what you are looking for. So, and you must know how the table you are going to use, how the area is defined. So why am I looking for 0.95? Because this table, it is the values that I'm supposed to read, they all start from minus infinity up to a particular value. That is why I was looking for 0.95. It is from minus infinity up to this z-score value. So when we looked at the table, we found that the z-score value, which is close to 0.95, was 1.64. And so when we substituted in our equation, then we find that our confidence interval is 52.92 up to 56.86. And usually how we answer that question is that we say that we can be 90% confident. After calculating our answer, as statisticians, what do we tell the general public? We tell the general public that we can be 90% confident that the population mean is somewhere between 52.92 and 56.86 and 56.86. So from this example I've done and the others that we're going to do, what I can say is now we are thinking freely. We have to understand the question, we need to know what we are looking for, and we need to know how the table that we are going to look at behaves. And this is why I described the normal distribution, T distribution, F distribution, and chi distribution. Because we have to know how those tables are, then that is when we can get the correct values that are required. Okay, so now let's look at another example. So this is an example where we use the normal distribution. And when do we use the normal distribution? When sigma is known. When population variance or population standard deviation is given, then we end up using the normal distribution. Let's look at the next one. The next example is confidence interval for mu when sigma is unknown. When sigma is unknown. In the first case, sigma was known, but now in our second example, we want to get confidence interval for mu when sigma is unknown. Now, the formula for getting the confidence interval is x bar plus or minus. You see, sigma is unknown. Sigma is unknown. So if it is unknown, we shall be given some data and we have to calculate sigma. And once we calculate sigma, remember that now we shall use the T table and it shall be X bar, the confidence interval will be given by X bar plus or minus T alpha over 2 S over square root of N. You see now, we don't have sigma anymore. Now we have S. S is sample standard deviation. We will calculate, and because of calculating sample standard deviation, then we have to use the T tables. So the example, so I gave you data sets. I will also display mine. The example is this: assuming data set 4 is normally distributed, assuming data set 4 is normally distributed, find the 90% confidence interval. Assuming data set 4 is normally distributed, find the 90% confidence interval. So we want to do that. We want to do that. So I can close the normal. Data set 4. Data set 4. Yeah, where is it? Is it opening? Yeah. Yeah, okay. So we can look at data set 4. Yeah. So data set 4, where we had 47, 59, 53. How many data items were they? There are 16. Data set 4. There are 16 of them. So now we go back to the whiteboard. We've been told that we have to assume that data set 4 is normally distributed. Then we are required to find 90% confidence interval. So first and foremost, we need to calculate S. And we had discussed this. So of course, to get S, first of all, you must get X bar, which you will find to be 55.1875. 1875. And then now, remember how we calculated sample variance, which was given by S squared. Remember how we calculated sample variance? So the sample variance will be 84.829. So what else do we need before we substitute in our equation? We have X bar, S, we know square root of N. We need to get T alpha over 2. Now, before we go to the tables, we know that the T distribution is also, it is almost like the normal distribution. It is symmetrical. The level of confidence should be 90%. So let me wrap that line because I want to show the region which is which has an area of 0.90. And remember, for t distribution, the t distribution is usually, we usually have t distribution, let's say t alpha, with n-1 degrees of freedom, n-1, where n is sample size. So for confidence interval, again, this is a case where we have 0.90, and so on the extreme ends we shall have 0.05 again, 0.05. Likewise on the left side. So now we need, remember that because the t distribution is symmetrical, if we have a t value here which is positive, we have the same t value here, only that it is negative. Now saying here is rather funny. So if we have a t value which is positive, separating 0.90 area with 0.05 to the right, we have the same separating 0.90 area with 0.05 to the left. So what we really need here, this area is alpha over 2, so we need t 0.05, but remember that we need degrees of freedom. So how many degrees of freedom are those? 16 minus 1 is 15 degrees of freedom. And so what will that be equal to? T 0.05 with 15 degrees of freedom. Because I had taught you how to read those values, but let me just show again. Let me just show again for clarity. I don't want some people to feel that they don't know and I'm not doing anything about it. So where are my tables? So which one? T table. I share my screen. So I was saying, if I go to the whiteboard, we are looking for T 0.05 with 15 degrees of freedom. T 0.05 with 15 degrees of freedom. So at 15, moving towards the right, I can see T 0.1, T 0.05, yes. Starting with 15 on the left, the first one value we read is 1.341, the next one is 1.753. And if I look above 1.753, I see T 0.05. So the value we need is 1.753, 1.753. Yeah, so now why don't we substitute in our equation and then we can find the confidence interval. So our confidence interval will be given by, now I am substituting in equation number 2. Equation number 2. So The confidence interval is given by x bar is 55.1875 1875 plus or minus T alpha over 2, 1.753 multiplied by S. What is S? S is square root 84.829 over square root of n, that is square root of 16, because our sample is of size 16. And so we find a confidence interval of 51.1515 up to 59.22. So as we stated for the first answer, then again we state that we can be 90% confident. We can be 90% confident that the mean lies between 51.1515 and 59.22 and 59.22. So you know you are at home, so nobody's rushing anywhere. So we continue with our third example. Confidence interval for mu1 minus mu2. Mu1 minus mu2. This confidence interval is also known as confidence interval for a difference in population means. You can see it is mu1 minus mu2. That is the mean of the first population minus the mean of the second population. So in some books you'll find they'll say confidence interval for a difference in population means. And you know, for this one, we shall consider three different cases. Are they three or two? Yeah. We consider three different cases under this confidence interval for a difference in population means. In the first case, when variances are known. When variances are known. When variances are known. That is when variances are given. That is why they are known. Let's look at, sorry. So what is the formula for this one? The confidence interval will be given by x bar 1 minus x bar 2 plus or minus z alpha over 2. You see the variances are known, so now again we shall use the standard normal plus or minus z alpha over 2 and sigma 1 squared over n1 plus sigma 2 squared over n2. So this is the formula that we shall use. So suppose we have the following scenario. What is the level? So suppose we have the following scenario. Suppose we are given that the sample from the first population is of size 13. The variance from the first population is 100. And x bar 1 is 31.4. Then we are also given that n2 is 7, sigma 2 squared is 80, x bar 2 is 38.1. And then we are asked to find the 95% confidence interval. Find the 95% confidence interval for mu1 minus mu2. Find 95% confidence interval for mu1 minus mu2. As I said before, population variances are given, so we shall use the standard normal. So let us see what value we shall be looking for from the tables. So now we know that the middle area is 0.95. And if the middle area is 0.95, it implies that the two extreme areas are 0.025 each. 0.025 each. Because to get a confidence interval, the extreme areas must also be equal, since we are looking for a middle 0.95 area. So we need to look for this z. We need to look for z 0.0 0.025, which refers to the area to the right of the z-score value. What does that mean? It means that when we go to the tables, we shall consider from minus infinity up to that z-score value, and the area we will look for inside the table will be 0.975, because 0.975 plus 0.025 will be equal to 1. So now we can go to now we need to go to the standard normal. We need to go to the standard normal so that we read that value. Standard normal. I think, yeah, standard normal. We need to read Z 0.025. No, not Z 0.025. Because it's the standard normal, we need to read within the table 0.975. 0.975. 0.975. 0.975. I can see from 1.9, I can see 0.97128. Oh yeah, there is 0.97500. If you move from 1.9 on the left, you will see 0.97500. What is at the top there? So we have 1.9. So it is 1.96. 1.96. So this z-score value we are looking for is 1.96. 1.96. And so we can substitute in our formula. Let me go back. I don't know. Yeah, I think it's that one. Oh, what happened? I double clicked, yeah? I double clicked. So this is our formula. So we just need x bar 1, which is 31.4 minus x bar 2. X bar 2 is 38.1 plus or minus, what is z alpha over 2? 1.96. And then square root. Sigma 1 squared is 100 over, what is n1? 13 plus sigma 2 squared, 100 again, no, 80. 80 over n2 is 17. It's not 17, it is 7. It looks like I'm reading my own things. And so we shall find, let me put brackets here. Please take care of those brackets. We shall find a confidence. There's a question. There's a question. I think somebody's asking about something. Oh, some people are not seeing what? People are not seeing the whiteboard. What happened? Okay, don't worry. Let me, okay, many people are not seeing the whiteboard. Ah, what? You mean I didn't share or what? Wow, I did not share. Sorry. So from where? Sorry for that. I didn't share. Okay, thank you for letting me know. Now, let me go. What did I show you? I think I showed you the normal. Sorry. I think I showed everyone the normal. I showed everyone the normal where I was saying 1.9, 1.9, where we saw 0.97500, and at the top there is 0.06. So that is 1.96. Then after showing that, so we know that Z alpha over 2, now I remember. After showing that, what I did was I came to that whiteboard and it's opening. Yes. I came to this whiteboard and then I wrote that Z 0.025 was equal to 1.96. And so because we were given N1, N2, sigma 1 squared, sigma 2 squared, x bar 1, x bar 2, then I went back to the previous screen where our formula was. So where is that screen where the formula was? I think it's this one. Yes. So our formula was here. Confidence interval for mu1 minus mu2, where we have x bar 1 minus x bar. It is x bar 2. X bar 1 minus x bar 2 plus or minus z alpha over 2. See, I'm trying to expand it a little bit. I don't want it to be too small. Okay, minus x bar 2. So I was substituting here. So where there was x bar 1, 31.4 minus 38.1 for x bar 2 plus or minus z alpha over 2, we read as 1.96, then square root sigma 1 squared is 100 over n1 is 13 plus sigma 2 squared is 80 over n2 is 7. So if we perform, and I said that there are these brackets here enclosing 31.4 minus 38.1. So we perform that operation first before we go to plus or minus 1.96. So then we find that our confidence interval is minus 15.27 up to 1.87, up to 1.87. And then again, we say we can be 95% confident that the difference between the two population means lies between minus 15.27 and 1.87. We can be 95% confident that the difference between the two population means lies between minus 15.27 and 1.87. So queries. Any more queries?